Let's consider some Brownian motion, which is a chaotic random motion of particles suspended in a fluid. Three-dimensional motion. And here what we have is we have some random motions here that we're saying could be a result of this Brownian motion. So we're going to have some displacement that has some I hat component, some j hat component, some k hat components. That's x, y, and z components to that. And it's followed by a second, a third, and a fourth. So we want to know what's the total displacement of the particle from the origin once you add up all these displacement vectors. I'm going to draw this as we go to get an idea on what's going on graphically, and then we'll add up all the components. So we want to find our total displacement, and we'll start graphically by drawing our x, y, and z coordinates. Here I've put x, y, and z. And now we'll start by looking at my first displacement and going positive 2 along the x direction, positive 1 along the y direction because we've got 1 times j hat, and then positive 3 in the z direction. And so the displacement vector there, r1, starts from the origin and goes to this point. We can then add, going tip to tail, from this point, we can add on another vector, starting from here and going onward. So that's our first vector. We will then add on the second one that goes in the negative x direction, 1, and then positive 3 in the z direction. So that's my r2. We can add on r3 similarly. This will be positive 4 in the x direction, negative 2 in the j or y direction, and positive 1 in the z direction. So that's my r3. And finally r4 should give us minus 3 in the x, plus 1 in the y, plus 2 in the z, and that's our r4. So our total displacement here is going to be the sum of all of these things. And there you go, that's all it is. So you can count up these x's and go, okay, so plus 2, minus 1, plus 1, 2, 3, 4, minus 3, and at the end you add those up. So this is just adding up all the I hat components, and 2 minus 1 plus 3 minus 4 will give us the result. And you do the same thing for the j hat displacements or the y displacements, and for the k hat displacements or the z displacements. Again, just adding up the components here. If there's something missing, for example, here we have an I hat, no j hat, but we do have a k hat, the j hat there is just a magnitude of 0. So that's where this 0 comes in. We can now do the arithmetic, and we get our total displacement from the origin is going to be 2 in the I hat, plus 0 in the j hat, plus 9 in the k hat. And the units of this are going to be whatever the units were initially of these lengths, which were all micrometers or microns. And so we'll write that as the Greek letter mu for micrometer or micron. Lovely. If we want the magnitude of that displacement, we can add these in quadrature. So we square them, sum them, and then take the square root of the result. That's how we get the magnitude of this vector. So the total magnitude is 9.2 microns as the total length of that vector. So we're 9.2 microns away. We could do some other geometry with trigonometry to get an angle, but in 3 dimensions, you might find it easiest to just stick with the x, y, and z components. Another thing I'll point out is that if we have 0 there, frequently what we'll do is we'll just omit writing 0 in the j hat, and we'll just include the components that are non-zero.